I will be introducing our two presenters today. We have Chris Webb and Dr. Dylan Ahearn. Chris Webb is a principal engineer with Herrera Environmental Consultants in Bellingham, Washington. For over 25 years, he has worked with many local and state governments, private and public entities, utilities, and nonprofit groups to implement stormwater quality projects and is recognized as a regional leader in green infrastructure design. Chris was the project manager and lead designer for the Park Place Stormwater Facility, which is the subject of this presentation. Dr. Dylan Ahearn is a hydrologist who has spent the last 20 years figuring out how best to eliminate toxic pollution in our waterways. He is currently an adjunct professor at Edmonds College and the associate director of water science with Herrera, Inc. Dylan specializes in green stormwater infrastructure with a particular focus on stormwater treatment research, development, and verification.
Well, thanks for coming. This project is probably one of the most, if not the most significant project in my career. I'm really proud of what we did here, and it was really, really meaningful. It was about 6 years of planning, science, and design from the beginning to the end, which we will summarize here in 20 minutes. So good luck to us doing that. But first, Dylan is going to speak about the initial science phase that developed the media that is used in the facility. And then I'll tell the story about the design. So we should just kick it right off.
Thank you, Chris. All right, I'm going to go back in the Wayback Machine a little bit. 12 years ago. Seems like a good place to start. Bioretention, at the time, it was just starting to be used more broadly. And it's proven over the years to be a very effective BMP, one of our most useful tools, right? Andrew talked about at the plenary session, the ecosystem services it provides with placemaking, habitat when it's used in the right of way, traffic calming, right? So yeah, the vegetation is great. It's a pain in the butt to maintain, but it adds all these benefits. On top of that, from the water quality perspective, it's very good at removing TSS, removing zinc. It's one of the few BMPs that's really effective at removing bacteria. Is there anything else that it's really good at removing? I think most of the people that know the answer to this question are in that room watching the presentation over there on an organic chemical that we know. Anyone in the room? Anyone? No? 6 ppdq, thank you. So there is limited data out there right now on what BMPs are very effective at 6 ppdq removal, but early indication is that bioretention is one of them, likely because of the high contact time. It has a low hydraulic loading rate, has high organic factor, lots of places to bind that chemical. This is a slide I borrowed from Jen McIntyre, and this is from Jen Utiana from just last year, a paper they published. And this was actually borrowed from a presentation that Jimin is giving next door. So I'm glad I'm giving some of the presentation for you, so you're not missing too much. But this is outrageous. Like, you see what's going on here, though? These are LC50s of different chemicals ranked from the lowest LC50. That means it's the most toxic to the least, but even the bottom row is pretty bad. Everything on this list is a pesticide, except for one plasticizer, which is put in tires. So really bad luck that Coho are so sensitive to this plasticizer. Pretty good luck that bioretention can remove it. It's one thing bioretention sucks at, and that's nutrients. And that's because the standard specification for bioretention is 60% sand, 40% compost. We all know that compost is full of nutrients. That's why the plants grow so well. This is a good thing. And it's fine if you have it with a bioretention system without an underdrain, right? If you're exporting some nitrate, some phosphorus in a dispersed fashion to groundwater, no harm, no foul. Once you start lining these things, putting in under drains, installing them close to sensitive water bodies, the export of that nutrients can become an issue. We first saw this documented about 10 years ago with the city of Redmond. They drink their shallow groundwater supply, right? And so they wanted to put in LID all over the city, but they were like, well, let's first check to see if the stormwater that goes through these systems and is eventually going to infiltrate is those pollutants from the street are actually going to be removed. So they had us do a study for them. And these are some of the data that came for that study. This is phosphorus in particular, showing the opposite of what you want to see. The influent here is blue and the effluent is red. You really want these switched. We were exporting a ton of phosphorus, in this case, into an underdrain in a line system. If that underdrain was going to a sensitive water body, you wouldn't want 5 milligrams per liter of phosphorus going there, right? And so when these data came out, people looked at it and they thought, and then ecology said, okay, let's pause for a sec and put out a little bit of warning, say, hey, don't install this stuff within a quarter mile of a sensitive water body, and give it a second thought before putting in an underdrain. In the meantime, let's research what some alternate bioretention media specifications could be that don't have this issue. So this went into about a 4 or 5 year effort of doing a lot of research. And we've presented some of this in past conferences, so I'm not going to go into it in depth. We got an ecology gross grant and teamed with King County and Seattle University, University of Washington, Western Washington University, a whole series of studies to essentially come up with these components that can be used instead of the 60-40 sand compost mix. And that is sand again, with coconut coir, biochar, and then iron filings and activated alumina. So that's the recipe we came up with. When we put that together in a mix, and this is just focusing on phosphorus, I'm only going to show this one data slide here, but the influent is the gray box plot, and so it's coming in at about 100 micrograms per liter phosphorus. We want that to go lower, right? That's our influent going into this column array. You see the 60-40 actually making things a little bit worse in terms of phosphorus, exporting the phosphorus. And then this one's great. That's really low effluent concentrations going on there. That's this treatment 4. And that's the one that we went with in terms of the ratios, and got this approved by the Department of Ecology, and you can get the specification off their website. We call it the HPBSM, High Performance Bioretention Soil Media. Meanwhile, in Bellingham, they're very interested in phosphorus up there. They have a TMDL for Lake Whatcom 2014. Yeah. And that TMDL says they need, in their developed areas, they need to sort of match forested in terms of phosphorus export, which means an 87% reduction in phosphorus from developed areas. That's a really tough target to meet. So they're looking for tools to reduce phosphorus. And, a lot of these basins that drain to Lake Whatcom are already built out. So they said, hey, Herrera, cool that the HPBSM is out there. We'd like to use that. But it's sized like bioretention, that's 6 to 12 inches per hour. We're doing this in a retrofit application. It would be a lot more efficient if we could have the same media doing the same workhorse media, maybe even better for phosphorus removal than the HPBSM, and at a higher flow rate. So that was like the marching orders. Go make something that does, more water and more phosphorus removal, because we want to put it at the end of a pipe in a regional facility, because that's the most efficient way to treat in a retrofit application. So those were the marching orders from the city. We went back to the lab and did this again. And, we were looking for a coarser aggregate to make things flow faster. Increase our activated alumina was a goal, to increase that orthophos removal. So actually removing the dissolved phosphorus is the tricky part. The total phosphorus, particulate phosphorus, that's relatively easy. So it's the iron filings and the alumina that are removing those. And we went back to the lab and tested it, like I said, got some stormwater, ran it through a whole bunch of different mixes with replication. It's great. Working with Western was wonderful. Some of their students are now working for Herrera full time, so that's great. Here we are, more data. Oh, I didn't think I was going to show more data. Let's just focus on the right-hand side, and these are percent removals this time, right? And so in this case, we want to be as high as possible on the chart. We're trying to get above that 87% removal. That's the benchmark. And these are different mixes we put in the columns, the different ratios of things. And we can see this one on the far right is the best. So that's way up there. That's like, what is that, 98, 97% removal? That one's great, but it had like 10,000% activated alumina in it. And activated alumina costs how much? $1,000 a yard. $1,000 per cubic yard or something. And so that one was a little pricey. That was the deluxe version. So we went with number 6 right here, which had a little less activated alumina. What that looks like finally when we compare the HPBSM spec to the post spec is for the main layer, there's this layer cake system. We have mulch on the top and then a primary layer and a polishing layer. Primary layer for the HPBSM is sand aggregate. And then for the post system, we're calling it now, phosphorus optimized stormwater treatment system. Did you name that? John named it. It's pretty good.
He didn't like
What was it? The Bellingham
phospholobster.
Phospholobster.
There's a reason.
A coarser aggregate, the same amount of coir and biochar as the HPBSM. Polishing layer is a little different. We like goosed up the activated alumina by 10% and the iron by a tiny bit. The trick with iron is it's amazing. It's actually good at metals removal, ironically, and it's also amazingly good at phosphorus removal, but it turns into a brick if you use too much of it. Like your whole media turns into a giant brick. So you got to be careful with that one. That was the column study. Now we wanted to take this thing and test it full scale in the field. So the city's objective here was to actually get a new approved BMP before they went and actually built the whole facility. So they're like, hey, Herrera, go test this full scale in the field, get it ecology approved through the TAPE program, and then we'll build it. So, okay, let's do that. I do a lot of that, so that's fun. We built this thing, and this is sort of what it looks like. It was a 2-layer cake system. The primary media was on the right, the secondary was on the left. We split it up so you can see sort of the efficacy of each layer independently, but you can build it stacked if you want. That's how we laid it out. Full scale tape testing, automated sampling, continuous flow monitoring. Here's Jasper out here helping us. That's Chris's son. Amazing billing rate, super efficient for the city. They really appreciated that. And we just flew through this project, got it approved. And we were off and running to actually build the whole facility. Chris.
All right. So being a media filter that's bioretention like, that's typically deployed in a distributed way, when we try and take that type of practice and we try and scale it up to a regional practice, there's a couple of problems that come up, and that's the focus of what I'm going to talk about. But the initial genesis, the germ of this idea came when it's a little bit of overlapping timelines, but the city had gotten an ecology SVAP grant to do a simple retrofit for 6 acres on Britain Road. And we came up with, it was a fully built out street with a lot of conflicts and expense. And we looked at a distributed approach there, and we came up with this $400,000 price tag, which rolled up to about $100,000 of capital cost per pound removed of phosphorus per year. In the city of Bellingham, their benchmark is $50,000 a pound removed per year, and that's based on what it costs them to buy a development right of avoided phosphorus generation from land development. So they know they can go out in the watershed and buy land at about 50K a pound and avoid phosphorus. And so we were 2x so there's an important cost and efficiency part of this story. So in looking at that project is kind of how this site turned up. We found this underutilized. It actually had been built out twice, rebuilt twice, built once and then rebuilt once as a regional facility. Back in 2005, it was originally an old wet pond, or in the late 90s, it was built as a wet pond, and then it was rebuilt as a large bioretention type system. Turns out it actually had some phosphorus export issues, and so we propose essentially rebuilding it for its third life using the post system. And so there's the site there. It's about 1/4 of an acre. And we also found that if we could do some basin modifications, we could direct about 1/3 of the watershed within the city limits of Bellingham to this facility. So in one go, we could get 1/3 of the Lake Whatcom watersheds, of the city's portion of the Lake Whatcom watershed into one facility. And we knew from the application rate that we could actually achieve that on this 1/4 acre site. And in running the back of the napkin, we figured out that we could build that project, and thanks to Ecology for funding it, at about $30,000 a pound removed. So 1/3 of the cost of the other project on a unit cost basis, and also well below the city's benchmark. So this was a win. This was the inspiration to go. We also know that there were some things that made this project cost effective. The conveyance was already there. It was already a stormwater facility. There were a lot of factors that made this a very efficient project. But the media performance and all that was a significant part of it, and centralizing O&M. So it's really again, the efficiencies of a regional facility. Then there are the 5 problems that we had to solve. And this is really the focus for me is that there are a lot of regional facilities that are designed using media filters that are traditionally used, like big bioretention and things. And there's problems that aren't problems when you design things in a distributed way that manifest as big problems when you start to make it centralized. Number one, and so these are the 5 that are the focus of what the problems were that were the driving our design and what our solves were for the problem. So one was manufacturing the media. This doesn't exist, it's never been built before, so we had to figure that out. We had to deal with modeling inaccuracies. WIM is fantastic and a great tool, but it has a lot of idiosyncrasies, particularly in this area about predicting the actual flow. And to achieve the high performance, we knew we needed to deal with some issues in WIM. We knew that bigger steep basins are going to generate a lot of sediment. We had to deal with that. And then really the last 2 are insidious problems with media filters that we were creating like a laser beam to focus on. One is flow distribution, right? Given the distribution of our rainfalls, with so many of our storms being small and prolonged, so many of our media filters are only engaging a little bit of media right by the outlet, 90-something% of the time, and that particle of media in the back corner is not getting engaged, and therefore we're hammering, and it's just not an efficient use of the media, and the theoretical sizing is not really applying. And then the last one is prolonged media saturation. So if you have a big basin, long duration storms like we have, and in particular in this basin where there were flow control facilities in the basin, plus groundwater, we knew we were going to have a lot of base flow and long duration flow, which could lead to the media being saturated, which can cause all sorts of problems in the degradation of the media, and it actually potentially giving up phosphorus and all of those problems. And so we set out in our design to solve those. So manufacturing the media, we ended up creating a specification based on the one that is in the ecology guidance for the HPBSM. That is the manufacturing on the left. The spec worked. That contractor decided to build it and blend it themselves. And then on the right is the Walrath facility, who's a contracting blender who's done most of the blending for the other times. That's the HPBSM being blended on the right and the post on the left. So it turns out we can make it. It turns out that the spec worked. We were able to get it made. To solve the modeling inaccuracies, I think we're circling there the ponds that are actually contributing to the long duration flows. We did a calibrated basin model. So we did a year of we did a year of flow monitoring, calibrated our basin model, and we're able to dial it pretty tight. So we knew that our flow splitters and other things that we had to design were going to be spot on because the site was extremely flat. And so we had everything was dialed down to minimums. And so we really, really wanted to know exactly what our flow regime was. We did put a vortex in to manage our sediment. We sized that appropriately to make sure that we can get as much of the big stuff out at the beginning as we possibly can. And then the especially interesting things. So to deal with problems 3 through 5, we did something that I don't think has been done in the region yet, is that we used a smart system. We used an active dosing system using a programmable logic controller operated set of valves. And we wrote an algorithm, and we were actually able to run the algorithm. My colleague Neil Shaner, who's a master at this stuff, I couldn't pull this off, but he wrote a program that we actually ran the algorithm many, many times to figure out what dosing patterns and regimes where we could achieve our treatment goals and also meet the criteria of not having any filter cell online for more than 24 hours. So we started with online for 24 hours and then resting. And then we also, through the use of the computer, can adaptively manage that based on actual conditions and performance and bypass on the monitoring that we're doing. So that we wrote an algorithm that was used in the model, and then also was then deployed into, this is the control panel, and the programmable logic controllers up on the left. This is all the business that the electrical engineers told me we needed to have to make it all work. And then we have a little touchscreen interface where we can completely control the system, adaptively manage it, changing the rest times and the dosing times to achieve our goals. We have a couple other really fun things. Once you can control systems in this way. It turns out you can run other experiments. And one of the things we did was to test out. One of the other questions in the industry is like, how much do the plants do? You know, because the post media can be in a planted configuration and an unplanted. So we were able to build into the PLC designating, we planted 2 cells and then we left the other ones unplanted. So we can actually, there's a mode of operation where we can run it planted only or unplanted only, and we're set up to do monitoring. And so we can compare the effects of that. So there's a whole bunch of really, really fun things that you can do when you have a brain at your stormwater facility. So really it was the use of that PLC then solved it actually solved the management of sediment, because what it does, we program this to drive the cells into ponding. So as the flow comes up, it's programmed to send like 100% of the flow to a cell, send it right to ponding, which we're going to push water over the entire surface area of the facility, max out its capacity before we turn on the next cell as the storm comes. And so that allowed us to solve also our flow distribution issue, because it's not a problem anymore. We're going to just drive that cell into ponding, and with something with cells this size and basins that big, we can do that. So our facility is going to be into ponding more often than a typical facility, engage more media, spread that sediment out, engage more mulch. And then also we can turn them off and address this prolonged media saturation question. And so in practical fact, what that looks like, I think this is an animation. Yes. In practical fact, you can see the valves there on the left. You can see the flows coming. We have a flow splitter across the street. It sends the water into the facility. It sends it into the, it's coming into, it's going to engage. It's real soon. It's going to, there we go. Now it goes into the vortex. You can see the little butterfly valves there on the left. Each cell has a corrugated polyethylene pipe with orifices on it on the surface to do distribution. It engages. This animation is running a little slower for this presentation, but it's, I guess, then the cells flood, engages in the under drain, and then there's our outlet manhole, and out we go. And then we also made it nice for the neighbors. There we go. And then I'll quit at this. I don't know if we have time for this completely, but we did time lapse the construction. I couldn't quite get my camera in exactly the right spot. We do have concrete walls that separate our basins. It's not lined, but we have some geotextile down there. There's a whole question about groundwater in the design that we could talk about. And that's basically the construction process. And then, yeah, there it is being built. But really the takeaways here is how efficient we can get a regional facility design, and then how by investing in smart technology and high performance media, we can really solve these problems. Because if we don't solve those flow distribution problems and prolonged media saturation problems, we're not going to get the performance that is theoretically shown in our idealized design. Okay, I'm gonna move us on here. There we go. And so there it is in the old kind of compost amended sand filter that was there prior. And so the neighbors, I think, looks a little nicer than it did out there. Oh, you surprised me. Yeah. This was going to be a picture of the facility built, but Dylan and I did go on a fantastic bike ride in the hills this morning, and apparently he changed out the photo. So that was super rapid fire. I'm wanting to leave time for questions, and so yeah, we'll look forward to any questions you may have. Thank you.